started. So I'm pleased to introduce Stefan Wehr, who's, don't be fooled by his professor title, because he actually has a long career and history in industrial software development. He's going to tell us a little bit about that.
Yeah, thank you, Mike, for introducing. Welcome to my talk, a software architecture based on coarse-grained, self-adjusting computations. And this thing is not working. So as Mike already said, I've worked quite a bit in industry, and that's where the motivation for this talk is coming from. Back in 2010, right after my PhD, I joined a company, and we were set out to solve the problem where you have lots of data being produced in hospitals, and doctors and nurses, what they want is a kind of condensed view of the relevant data on mobile devices. And because wireless coverage in hospitals, at least in Germany, was back then very problematic and still is problematic, these mobile devices should work offline. And clearly, if some input data changes, and there comes a new radiology image, whatever, then these changes should be propagated rather quickly to mobile devices. And that's what the company was started for, develop a commercial software product for bringing these data not only to the doctors and nurses, but also bringing them in a nice, condensed, sensible view. And before I tell you something about the architecture of the system and give you a demo, I will briefly recap two possible options how to design such a system. The first option is pull. That's quite simple. Mobile devices would then periodically check for new documents, and then the server would compute these documents and send it back to the client. This could cause a lot of redundant work if inputs remain unchanged. There is latency introduced by the poll interval, and also offline is quite hard to support efficiently with this pull approach. And the other obvious candidate is push. So if there arrives new input data, then this triggers a recomputation and some sort of synchronization, send the aggregated documents to the clients. Well, with this approach, offline mode, you can implement offline mode quite efficiently. There is no significant latency except for the time it takes to process the changes and to compute the new documents. There is no redundant work when some input changes. On the downside, well, you waste work if input changes rather quickly and nobody observes these changes, and you do just wasted work. And you need some sort of framework if you want to use such an approach. Yeah, you won't do dependency tracking and all this stuff by hand. And basically, the talk is about the framework we developed for this purpose. So I will report on this framework written in Haskell. I will give you some insights into the architecture of the framework. It's on the slide, but it's more on the system where the framework was put to use. And I will also report on about 10 years of experience using this framework and using this software system in a commercial software product that has been used and is still being used in several of the largest hospitals in Germany. The whole framework and also the demo I will show you is open source. You can find it online on GitHub. So basically there are kind of three parts of the talk. First I will show you the API and the demo of the framework, and then we'll come to the commercial application that's using this framework, and then there is a discussion at the end. Maybe some background information, because the title of the article contains the term self-adjusting computations. Maybe not everyone knows what this means. It's pretty simple. The change of inputs should update the results automatically. Then needs to be some kind of dependency tracking in place, and you must cache intermediate results. in the research literature you find about self-adjusting computations, the updates are rather fine-grained, so individual list elements. For our approach, you will see that data updates are much more coarse-grained. So here's a quick example. If you have these three inputs, then you could somehow accumulate them, produce some intermediate results, and from an output. And if one of the inputs changes, then you only recompute the relevant parts. Well, I think that's pretty much it. So before we come to the real application, I have, well, basically what I did, I wrote a kind of stripped down version of the application, and that's what you find in the GitHub repository. So that's the architecture, but maybe I will show you first the demo before we discuss this thing here. Where is it? Here. So that's the browser showing the demo. You see it's not very beautiful, and it's also very simple. So what you have here, you have basically two views. You have a list of patients down on the left. They're all patients, where you can find all patients in the hospital, and the recent patients are those patients which have been admitted recently to the hospital. And if you click on one of these patients, then it's self-loading because I didn't start the pipeline, then it will show details. So let me start the pipeline. What do we have here? Let's start. No, what's this? Oh, that's the web server. And what do we have here? There's some kind of simulation which basically simulates the data being produced by the hospital, and then there's finally the processing pipeline which reads data from the hospital and produces the output that then becomes apparent in the browser. So I think so. Okay. There are no recent patients at the moment. Maybe this is a configuration issue because. Sorry. Okay. Okay, then it was just still starting up, or maybe the simulation didn't produce a recent patient at the moment. What I want to show you before you go back to the slides, there is some configuration going on because in the real system there are also lots of parts that are configurable. And you see here, maybe I make it a bit larger. There's one option, recent time, and that's the time after admission to the hospital where a patient stays in this list. So for example, if we now change this to 0, then the list of recent patients should become empty, and you see it changes rather immediately, because the change of the configuration is propagated to the system, and then the list here of recent patients becomes empty. Okay, so far so good. So if there's anything unclear, just ask directly. I mean, you don't have to wait until the end. Where do I need to go back here? Yeah, sure.
So exactly in that moment when you change the 0 hours to 12 hours and back, like, I'm curious what the computational complexity of that incremental update is, right? Because like a naive, in a self-adjusting computation system, like, those things typically don't naturally look at history. Like, do you have to like re-inspect all the patients to like look at their time and figure out, or is there more efficient implementation of that?
I'm thinking whether we will see this in a minute in the code. Basically, it works by caching some things, and then the data is in memory. And yeah, you have to, in this case, we filtered a list of all patients to produce the list of recent patients based on the time.
And so when you change the time, you just do a full scan.
Yeah, you rechange the list of, I mean, not the list of all patients with respect to the total history, but with respect to all patients that are currently admitted to the hospital. Yeah, we have to rechange it. Yeah, that's what I mean with coarse-grained. If you look in the literature of self-adjusting computations, then you can really do updates on the granularity of individual list elements, and that's not what we are doing here. Okay, so that's the architecture of the demo, and I will show you on the next couple of slides how the demo has been realized in Haskell. So you see here basically three sources of data. There's here something called import store. That's an event store for data coming from the hospital. So this import store contains data about patients, data about medical reports. I think for the demo I didn't model medical reports, so it's basically only patient data. Then there's here something called workflow store. That's where interactive data produced by nurses and doctors goes into. So if a nurse puts down some note for a patient, then this data enters this workflow store. And there is the configuration. You can configure various aspects as we've just seen before. And these three sources of data, they flow into this pipeline of self-adjusting computations to produce here for demo, they produce directly a model for the UI. This component is called a file store. That's also some kind of event store. And then the HTTP server sends the data to the web browser. Okay. So, and I will now show you, there's a screenshot where you can see the three parts of the GUI, but we've already seen that. I will now show you how the main things are realized in Haskell using this framework. Because I mean it's using a framework, so there are some things which you need to know from the API of the framework. So that's the computation here on the top for reading the configuration. So before you can use a computation, you have to define it. Define comp defines a computation. You give it a name, and then there's a caching strategy. I will explain two different caching strategies later on. And basically, this part here is then the body, the logic of the computation. And from the type of define comp, you see here, that's the type of the body. P is the parameter of the computation. R is the result, and everything is running in this comp M monad. And you get back a compdef value from define comp. And what you also see in the body here is comp source rec. That stands for computation source requests. This comp source request issues a request to a computation source because the framework abstracts over different kinds of data sources where input data comes from. And in this case, file source is some source accessing files on disk, and read file is a request to read a specific file. Okay, so that's quite simple, getting the configuration. Then the next part is how to generate a list of all patients. We do this in two steps. In the first part, we do an over approximation. It's basically a fold over this import store, over the event store, and we visit each event only once. And we do it in two steps because in the first step we don't want to depend on a configuration, because depending on a configuration might mean we have to visit an event a second time, and that's something we want to avoid. So, and folding over something, there is a second kind of function for defining a computation. Define inc comp defines an incremental computation. That is a computation that is feed again and again with data keeping some intermediate state. Basically that's the initial state, and then the F does the fold, consuming new events from the import store and updating the state of the fold, producing a new state. Okay, and then in the second step, we compute or we generate the real list of all patients by taking the configuration into account, because it's configurable how long before admission and how long after discharge a patient should be visible. And with this, you see that such a computation definition here can refer to other computations. So this computation definition is parameterized over the computation for accessing the configuration, and that's the computation defined on the previous slide for generating the complete list of patients. And then what we do in the body here, we call these computations. This is eval, comp, or fail stuff here and here. we can access the time at a certain granularity, and then we filter the complete lists of patients with respect to the configuration and the current time. So that's basically the filtering here, and yeah, and that's the complete list of patients that are currently in the hospital. Okay, good. So far so good? Okay. So then there has to be some wiring to bring all these computations together, because we have seen on the previous slide, certain computations can accept other computations as arguments. In our framework, you have to wire them explicitly. There is a monad comp wire M for this, and that's how it looks like. I mean, you take the computation definition, you take a computation definition, or maybe we look at here, wire comp takes the computation definition and gives you back the runtime representation of a computation, and this thing you can then pass here to other computation definitions to drive the wiring. Okay, so that's basically how the framework in general works. For the demo, there are also some computation for generating the outputs. I've omitted these because it would be too long and probably also too boring. And there is also a type class called compsync, which is abstracting over the outputs. So we have abstraction facility over different input sources, and there is an abstraction over different kinds of outputs. And the output of this demo, at least, is the UI model of the application, and yeah, basically it's a simple kind of markup language, which for the purpose of the demo I just modeled with Haskell data types. So we have a document here which has a title. SL is a strict list of sections, and a section has also a title and a list of content, and so on and so on. One thing I want to talk about briefly is caching. The framework caches intermediate results, and there are two main modes. The first is full caching. Then this means the full result of a computation is cached, so that the result can be reused if the same computation is called again with the same arguments. Clearly, there's always, if you choose full caching, then you have to do some sort of trade-off between how large is the result and how much time takes it to recompute. So that's up to the user of the framework whether he or she uses full caching, or the alternative is hash caching. There we do a large hash, or we compute a large hash value from the result of the computation and only cache this hash. Clearly, then you need to re-execute computation calls when they are called again, because we don't have the result in the cache, we only have the hash. But it's useful as a kind of dependency blocker that's very used at some places. So if computation C1 calls C2 and C2 calls C3, and here C3 changes, but this change does not cause C2 to change, then you don't have to re-evaluate C1. That's what I mean with a dependency blocker. Okay. So basically that's what I want to tell about the API and the demo of the framework. And now I will report a bit on the experience I made using the commercial, or using the framework in a commercial application. Maybe first some background on the application. It's as you've seen, a health information system. It's used in several larger hospitals in Germany. It has been developed and is still developed by a small company in Germany. Users are doctors, nurses, and there are also patients using the app. There are two front ends, web and mobile. There is an offline mode, as I said at the beginning. And the application has, I would say, 4 main features. So you can access the electronic health record, the EHR of a patient, in a read-only fashion. You can write some fields of the EHR. These are 2 features, and the other 2 are it allows collaboration between doctors and nurses, so they can exchange messages and so on. And it also allows patients to communicate with the hospital. So how does the system gets the data from the hospitals. Hospitals, at least in Germany, I don't know about other countries, but I could imagine that it's similar elsewhere. So hospitals in Germany, they store patient data and other data really scattered over different sources. So this piece of information you find in this system and some other piece of information in some other system. And that was really the initial motivation for providing a system which somehow aggregates information from different sources. And two main sources are HL7. That's the standard encoding patient data, patient reports. It's an event-based system. That's the main point here. And another thing is HL7 is meant to be the standard, but every hospital I know uses its own, let's say, dialect of the standard. And then another important standard is DICOM for accessing medical images. This is a query-based data source. And there can also be various hospital-specific systems for accessing whatever kind of information. Here are some numbers. I asked my former colleagues to look at a large system to give me some numbers of the current state of affairs. And this is what they sent me. So 140,000 HL7 messages per day with 1.6 terabyte of disk space, 10,000 patients, 230,000 reports, 6.5 million DICOM images, and only 500 users. That's because not all doctors and nurses in the hospital are using the installation where my colleagues looked at. Probably also interesting is the implementation uses several languages. Clearly Haskell is mainly, the backend is mainly used in Haskell, but we are also using quite a lot of TypeScript code for doing client-side scripting. Then there's Objective-C code for the deprecated iOS client, and we have Dart code for the new mobile client.
75,000 lines of Haskell.
Yes.
That's probably the biggest Haskell program in the world.
I don't
A
know.
lot bigger than GHC.
That could be.
That's a lot.
I counted the lines by myself. It includes comments, but there aren't too many comments, so that should be. Okay. So that's the architecture of the whole system. It's a bit more complicated than for the demo. So, and there are basically 4 steps, and I will now explain them individually, reusing parts of this graphic here. So I won't explain everything on this slide, but go part by part. So the first part is the import. How does data comes into the system? I've already said there are various data sources in the hospital, and that's why also the framework provides an abstraction for data sources. For example, there's a communication server which in a hospital, that's part of the hospital IT infrastructure, and that's here our system. And this communication server, it sends out HL7 messages on various occasions. A new patient is admitted, patient is discharged, and so on. And then we have here an import component. For DICOM, we have another component. And you see here, HL7 is somehow event-based, so the communication server sends a message to our system, whereas DICOM is query-based, so our system queries here the DICOM server in the hospital. The next step is then interpretation. The purpose of the interpretation is to bring hospital-specific data formats into our domain model. You could now say, why does every hospital has its specific data format? Well, I don't know, but that's the case. Essentially, all data formats contain the same kind of data, but it's different. And that's why we bring it here into our domain model. So for example, that's part of a HL7 message. CRP, it's some inflammatory value, and it then gets transformed by the interpretation, here driven by self-adjusting computations into our domain model. Now you see here the domain model is then persisted So this blue thing is a persistence layer. It's persisted in a component called file store. The file store is essentially a multi-version document store. It works similar to an event store, or it has certain functionality of an event store, but it deletes unreachable data after a certain amount of time, because otherwise we would simply run out of disk space. Okay, so far so good. The next step is then take the data from the domain model and map it to the UI model, which then can be synchronized to the users. And that's here. And I mean, that's now pretty similar to what we've seen before. There's also this workflow store where user input is stored, and from the workflow store, the file store with the domain model, and from various configuration files, a pipeline of self-adjusting computations compute the UI model. And here, the CRP example in the UI model would look like this. You see here, there is no meaning whatsoever of a laboratory value called CRP. It's only a key value cell, and the rendering could then look like this. There's also an export manager which brings back certain data into back to the hospital. Okay, and finally, well, that's now pretty simple. There is a synchronization component which reads from the file store here. It's an event store, so the synchronization server gets events, and then it has to compute which document needs to be sent to which client, and it does so. Okay. So that was basically the architecture of the whole system, and now I've prepared some slides with hopefully useful insights I gained during the 10 years where I was working with the system. As I said, the development started back in 2010. It's still alive, meaning it's still running in several hospitals. And from my point of view, I can say the framework was flexible enough over the years so that we could add several extensions. So we added these export functionality you've seen on the previous slide, on 2 slides before. We've added at some point later. We implemented something called demand-driven generation of outputs. I'll talk about this in a minute. At some later point, we've added client-side scripting later. So it turned out to be quite flexible. Clearly, when developing such an application, there are other aspects besides computing the correct kind of data. So privacy, security, regulatory affairs, deployment, whatever. But for this talk and for this paper, I ignored these aspects. They're important, but not for this talk here. Okay, so from my point of view, the computation framework has shown several benefits. So first of all, it provides really the foundation for supporting offline mode. So you need to pre-compute the documents if you want to have a true offline mode. I mean, you could always do offline with some sort of caching, but then users could only access those documents that they've accessed at some previous point in time. What we've also seen is it was very good to have no redundant computations if user access the same data multiple times, because that's what's happening in hospitals. The users they are looking at the same data, or various different users are looking at the same data all the time. And if you would recompute it every time someone looks at it, this would be much too expensive. And it also scales well with the number of users. So if you add a new user to the system, there is not much work to be done because everything is already computed, at least if the new user has the same view configuration as an existing user. So if each user wants to have its own fancy view configuration, then it becomes too expensive, but that's why we try to keep the number of view configurations quite low. Clearly, there are also disadvantages. The biggest disadvantage, at least the way we implemented it, is long startup times. So if the system crashes, which really happens rather rarely, but also if a system needs to be updated, then it takes quite a long time until it's up and running again, up to 2 hours here, and that's why, because the internal state, or we did not persist the internal state of the computation framework. I mean, you could do it at some point. We tried it, but then something else became more important, so we suspended the persistency layer. So I think it's not impossible to do, but we just didn't do it. Also because 2 hours sounds really pretty bad, but the system is still kind of working during this time. You can access all data in a read-only way. You can also enter new data, but you won't see any new data coming into the system. So that's not really good, but it's not that the system is completely down and you cannot access anything. Okay, so another disadvantage is what happens when the number of inputs increases. Let's say the number of inputs doubles. Number of patients, you have twice as much as patients as before. Then clearly you need to do at least twice as much as work as before. And this at some point really became a problem. And then we realized, okay, many of these patients, they are not accessed very often. So there are a certain set of patients, they are accessed all the time from our users. And another set of patients, they are really accessed only very rarely if they have night shift, for example, which only happens 2 times in a month or so. And so we said, okay, for these kind of patients, we generate the outputs on demand. So only if the user clicks on one of the patients, then the whole data set for the patient is generated. Clearly, these patients aren't synchronized for the offline mode, but nevertheless, it was a good trade-off. Okay, so there's one slide comparing push versus pull. What you can, or what's the case? Pull does work per client-side request, and with the push approach, you do work for every input change and for every output. And if you want to decide for your application whether you want to have pull or push, then then you have to look how often does input data changes, how many client-side requests do you have, and how many outputs do you have. For our application, it's the case that update rates in hospitals are rather low. So here five updates per second, but most of the time much lower. Many outputs are accessed frequently, so that really means the push thing here works out pretty well, especially if you combine it with this on-demand generation of outputs that are only rarely used. So one last slide about Haskell. Is Haskell important, or could you do the system in another language? Well, I think you could do it. Also in another language, there is nothing especially important, or it's nothing that prevents you implementing it in another language. But having control of side effects in Haskell is really nice, because these computation bodies, they are re-executed at some later point in time, so you don't want to perform arbitrary side effects, because those would be just repeated. And we also use the free monads trick to suspend computations. Laziness in Haskell is sometimes in the way. I mean, we all know space leaks triggered by too lazy data is a problem. So at some point in the project, we decided to use the strict data flag. So in the whole project, all data types, all fields of all data types are strict by default. There are some data types which are explicitly marked as lazy, but not very many. And sometimes, or not only sometimes, monitoring the execution of a Haskell program can be really challenging. If you want to know what's going on, then it's not too easy to answer. At least back when I was working with the system, I think such things also improve over time. Okay, so short summary. What I've shown you, software architecture based on self-adjusting computation, implemented in Haskell in development and operation since now 13 years. The software runs in production, and you can access the framework. And I mean, it's not the original framework. I simplified it slightly, but it's taken from the production code. You can access this in the GitHub repository, where you also find the demo code. Thanks for listening, and feel free to ask any questions.
Thanks. Every time I hear somebody talk about incremental computation, I think this looks like a build system, and every time I see somebody talk about build system, I think like this looks like incremental computation. Is there a fundamental difference between these two, or why could you have used Shake, the library, inside the thing and would do the same thing, or?
Yeah. So in the paper there is a discussion about the similarity between Shake and our system. Actually, I'm not totally up to date whether Shake now supports in continuous mode. But back when I was working on the system, Shake was simply executed, run it, and then it's done, and that's it. And our system is running continuously, watching on changes of inputs, producing new outputs. I mean, there are also build systems which do exactly this task, running continuously. So there's definitely a large similarity. True.
Hi, Stefan, thanks. You started off telling us about pushing notifications from the data store to the clients, and then on the diagram sometimes there's updates sometimes of some fields somehow go back to the data source again. There was this kind of out-of-band error for sending, I forget what slide it was. You had there we go, 2 slides forwards from that. Oh, well,
so
from the export manager back to the hospital,
yeah.
Yes. So there's no connection between the sort of read view and the write view of this data. The writes just go back somehow. Maybe they're sent by post, and sometimes somebody in the hospital opens the envelope and puts the thing back. I mean, did you? It looks like it wants to be a lensy kind of thing, where you present on the mobile devices and the web browsers not just a view of the data, but allow people to update the data or update some of the fields of the data, and that you could have a more principled connection between the reads and the writes.
Okay. Now that's a good question. I think the answer is life is quite simple, because the data we send back here, it's sent back as a PDF or as PDF that's archived somewhere, and that's it basically. Right. So yeah. It would be cool to have some kind of interactivity where a user fills out a form here and gets sent back to the hospital, and other data are integrated into the same document and then sent back to the user. Well, but it's not as complicated as this. Yeah.
Some of the red arrows could be bidirectional things rather than just unidirectional things.
If we would need this kind of extended functionality, yes, but really this arrow here is only
PDF.
Send a PDF to some archive, and that's it.
I wasn't so far off with the envelope.
Yeah.
Any other questions? We got plenty of time.
So one of the interesting things about self-addressing computations is you have bind, and bind gives you the ability to like dynamically reconstruct parts of the graph in response to changes to configuration or changes to data. I'm curious how that dynamism did or didn't play out in the design. Did you like depend on the ability to kind of dynamically reconfigure the graph?
What do you mean with dynamically reconfigure the graph?
So you can imagine a system just like this, which just uses like the map-like parts of the monadic interface, so in applicative rather than a full monad. And in a system like that, the structure of the graph is known statically when you construct it, right?
Yeah.
Once you have a monad, not so much. Now the bind can refire at some point in the middle of the computation, and you can construct a different subcomputation.
Yeah.
Right. So you could have something which at startup depends on 5 different inputs, and then like something changes. Like no, now I want to depend on the totally different 50 set of inputs. Yeah. You can reconstruct the graph as you go. And I'm wondering, like, was that dynamism important to this application? Or could you have gotten away with a more static graph?
No, it's important to the application. For example, I mean, you can change in the configuration, you can change all sorts of things, which can, for example, enable a complete new kind of view. And for this new kind of view, you need to fire different computations. Yeah, so you need this dynamism, definitely.
Any other questions?
I'm impressed by the size of the project, and I would like to ask how far did you go with the stronger typing here? Where is the balance to get too far with it, or there is some balance that is good for the teams to work on such a big project in some simpler way or something like that?
Yeah, very good, good question. This is more Haskell related or type system related. So my point is keep it simple, stupid. So really only use the basic things of Haskell's type system. We have some type classes for serialization, for pretty printing, all the basic stuff. Algebraic data types are used quite heavily, but we don't really use more advanced type system features.
And very few type classes.
There are not too many type classes, right? Yeah. So yeah, basic for pretty printing, serializing, maybe 2 or 3 other purposes, but not too many. Yeah.
Thank you.
All right. Well, let's thank Stefan again.
Thank you.